Dear friends, students and learners, I am Shashank Srivastava from SOET IGNOU. So in the previous modules which we have covered, we have completed up to the ferrous alloys in the unit 2. So from now we will take up the non-ferrous alloys and their properties and applications. So what are the advantages of these non-ferrous materials? So in certain cases these non-ferrous materials present the advantages of high strength and low weight in comparison to the ferrous alloys, and for certain other cases they surpass the mechanical strength of ferrous metals. So you can see that even they can surpass the strength of ferrous metals, and these non-ferrous metals are coming into demand nowadays because of good mechanical, electrical, good thermal conductivity, also different properties, and elevated temperature and corrosion resistance also. In certain cases, the non-ferrous metals like copper and aluminium alloys have no alternative in wide range of steel. What are the applications of these? These are very good for electrical conduction and aircraft bodies also. And we can see that a typical jet turbine, even the engine there in the jet turbine, it contains around 38% titanium, 12% chromium, 37% nickel, 6% cobalt, 5% aluminium, 1% niobium and 0.02% tantalum. Nowhere you can find iron here. So even in jet turbine they are used extensively. Typically aluminium alloys are used for cooking utensils. We can see in our houses all vessels are made of that generally. Also in aircraft bodies because it is lighter in weight, and as well as in building materials. Copper, it's a very good electrical conductor and used in electrical machines and power transmissions. Copper alloys are also used as tubing wherever good thermal conductivity is desired. So copper has both properties, good electrical conduction as well as good thermal conduction. Aluminium, now the first non-ferrous material we are discussing is aluminium, and a little bit of history. It was produced in 1825 and presently it is produced in quantity second only to steel. So it is that much important, and it is one of the most abundant metallic element found in the Earth's crust, and it is around 8% of the Earth's crust. And how it is made, we can see bauxite. Actually bauxite is the raw material, anhydrous oxide of aluminium and several other oxides, which is the principal ore of aluminium from which it is extracted. Aluminium is extracted from its ore mainly through electrolytic process. Now this electrolytic process, so the ore is first washed off. Why? To remove the clay and the dirt, because it is taken from the jungles and wherever it is in abundance. So all these things will be there in addition to the ore. Then it is crushed into powder form. After cleaning up, it is crushed into powder and is treated with hot sodium hydroxide, that is caustic soda or NaOH chemical formula, and this is done to remove further impurities. Alumina, this is the oxide of aluminium, Al2O3. It is extracted from this solution now and is dissolved in molten sodium fluoride and aluminium fluoride bath at 940 to 980 degrees centigrade. This mixture, after dissolving in the mixture of sodium fluoride and aluminium fluoride, is subjected to direct current electrolysis by passing direct current between carbon anode and cathode. So both anode and cathode are made of carbon. The metallic aluminium forms in liquid state and will sink to the bottom of the cell. So this was the whole process, and finally we have got the metallic aluminium, and this liquid aluminium is tapped off from the vessel from time to time. So this aluminium which is now obtained is 99.5 to 99.9% pure, with iron and silicon as the major impurities. So it is quite pure, around 99.5 to 99.9, but still it has the iron and silicon as major impurity. So this aluminium is then taken to large refractory line furnaces for refining before casting. So we again, like in the steel process and cast iron process, iron process, we now see that even aluminium is taken to furnace for refining. The chlorine gas is used as purging agent in the furnace to remove the dissolved hydrogen gas, and the liquid metal surface is skimmed off to remove the oxidized metal. So both hydrogen and oxygen can be detrimental to the aluminium. That's why they are removed, and the process is known as purging. It is done by the chlorine gas. The molten metal is then cast into ignores. Ignores we have studied in case of steel also. There are solid things, and this ignore actually is used for remelting or rolling. So there are different kinds of aluminiums then, and then we discuss now the wrought aluminium alloys. There are alloys of aluminium also. The first one is the wrought aluminium alloy. The preparation processes like sheets and extrusion ingots are cast through semi-continuous direct chill method. So this is one method, direct chill method, and these sheet ingots are then scalped, meaning if you see your skin is there, so somebody removes your skin, then it is a kind of scalping. Similarly, a layer of this ingot is also removed, so this is scalping. So by this scalping, about 12 mm of ingot surface is removed. The scalped ingots are then preheated to homogenize the structure by heating to a high temperature and soaking there for 10 to 24 hours. So this process takes place of preheating and keeping it at that temperature and soaking it for 10 to 24 hours. This preheating is done at a temperature below the lowest melting point of the constituents. Then these ingots are hot rolled and reheated several times till the desired thickness is achieved. So hot rolling and reheating will take place depending upon the type of thickness we need in our specimen. The products obtained this way are known as the wrought alloys, and they are normally in the form of sheet. Because we were using the rolling process, obviously they will come in the form of sheet or plate or rod or wire and extruded sections. Wrought alloys are identified by a 4-digit code. First digit will signify the aluminium purity, if pure aluminium is there, or the major alloying element. So the first digit signifies this thing, either aluminium purity or the major alloying element. The second digit will indicate the modification of the alloy. What kind of modification we have done will be given by the second digit in the 4-digit code. The third and fourth digits will indicate the minimum amount of aluminium in the alloy. So what is the minimum amount of aluminium present in that alloy will be given by third and fourth digits. So there are aluminium cast alloys also. So we discuss it now in this section. Aluminium alloys are cast by many processes, and these are given here. Sand casting is one. It is the simplest and most versatile process for small castings and complex castings with intricate pores. So if there are intricate shapes and pores, then sand casting is the best process. Large castings and structural castings are produced by sand casting with equal ease. So even if you have large casting or there is a certain structure, then also this process is very good and it is easy to do. In case of permanent mold casting, this is the second process. A metallic mold is used which may be gravity filled. Earlier in sand casting there was only sand. Now we are using a metallic mold, and this is filled with due to the gravitational force or due to the rotation due to the centrifugal action. So these are the two forces which are acting for filling up the mold in the permanent mold casting. The castings from permanent mold then are fine grained as compared to sand cast process. So better casting we are getting in case of permanent mold only, not in case of sand casting. Sand casting was easier, but permanent mold gives us better casting because it is giving us fine grained material. Then there is the process of die casting also. So if we need a high production rate, then this one is the best. The molten metal is forced into the die, which is a split but sufficiently strong to withstand the pressure. And what are the characteristics of die casting? It has close tolerance in parts and it also gives a fine grained structure, and the process is automated. So these are the advantages of die casting over other kinds of casting. Aluminium casting alloys need such element for alloying which will not only impart mechanical strength but will also increase the fluidity and feeding ability. So when we are doing the casting process, we need this fluidity and feeding ability. So that's why other alloying elements are needed. Hence the chemical composition is different from the wrought alloys. So what are the elements then? Like silicon, it improves the fluidity and feeding ability as well as the mechanical strength. Normal silicon content in aluminum is around 5 to 12%. Magnesium will be in the range of 0.3 to 1%, and it provides the strength mainly through precipitation. Also the zinc and tin and titanium are also present sometimes. And what are the properties of these aluminum alloys as such? They have low density and high electrical and thermal conductivity, which is next only to copper. And they have good resistance to atmospheric water and seawater corrosion also. And they are very much machinable, and formability and castability is also good. And it maintains good light reflectivity also. And they are non-toxic, non-magnetic and non-sparking. And how we can make this aluminum further strong? So the process like this, strength can be increased by the process of strain hardening and also by several heat treatments. Aluminum is used as a matrix in several fiber reinforced composites. Aluminum oxide as such is very hard and strong, and thus can be dispersed in the matrix of aluminum. By what process? By powder metallurgy to produce sintered aluminum product, which is also known as SAP. And then there are other reinforcing elements also used in softer aluminum matrix, that is boron whiskers, stainless steel fibers and whiskers of aluminum nitride also. Further we discuss the types of different aluminum alloys. These are divisible in three groups, that is the cast aluminum alloys, wrought aluminum alloys and aluminum composite reinforced with fibers or particles. We have seen this in just a few minutes back also, and now we are discussing again. So cast aluminum alloys, what are the properties? They have low melting temperature and they are insoluble to gases except hydrogen, but they give good surface finish. So these are important. And what are the drawbacks? Drawbacks are that shrinkage after solidification is there, and hence we have to be careful while designing the mold. And its mechanical properties as such are inferior to wrought alloys except in the case of creep resistance. And what can be the solution or the uses of these drawbacks? What can be the solution for these drawbacks and further applications? Like silicon, copper, magnesium and tin increase fluidity when casting thin sections. Mechanical properties of cast aluminum alloys is improved by adding copper, which induces age hardening to impart hardness and stability up to 250 degrees centigrade. Y alloy is also there, which contains 4% of carbon and 2% of nickel, and these help to retain strength at high temperatures. And this Y alloy is generally used in case of piston and cylinders of IC engines. So it is a very important thing, and mass production is there. Then the wrought aluminum alloys. These are obtained by addition of two elements, that is manganese and magnesium. So the aluminum manganese and aluminum magnesium alloys, these can be heat treated. These have high ductility with excellent corrosion resistance, and their applications are in like beverage cans. We see different types of juices and all, they come in cans, so they can be used there. And in cooking utensils in our kitchens and all. Then roofing sheets at the top of our roof and terrace, we can place it. So these are different applications. And further we move on to the aluminum composites. So AL alloy responds to heat treatment by a process called age hardening. So it can be alloy of aluminum copper or aluminum copper manganese and aluminum copper magnesium and aluminum magnesium silicon, different things. Duralumin is one such composite, which is an alloy containing 4% of copper and small amounts of magnesium, manganese and silicon. After heat treatment, this alloy develops ultimate tensile strength of 450 to 550 megapascal, and it is very commonly used in aircraft structures. So you may have learnt in your general knowledge also, sometimes it is asked. Duralumin is a very common word and a very famous thing. Apart from cast and wrought alloys, the greater tonnage, about 85% of aluminium, is used in commercially pure form, in which impurities are less than 1%. So aluminium extrusions then, like tubes, rods, wire, electrical conductors, chemical process equipment, foils and many architectural fittings, are made in commercially pure aluminium only. Now we discuss a very important thing in case of the aluminium alloys, which is the age hardening. So what is this? In certain alloys, actually precipitation from a single phase may occur. There may not be 2 or 3 phases, only a single phase. So this precipitate phase may be in the form of fine submicroscopic particles, which are distributed both around the grain boundaries and throughout the grains. So like when you see a microstructure of a certain material, so there are grains and then there are grain boundaries. So around these the precipitate phase is there. In certain alloys of aluminium, copper, magnesium silicate and beryllium copper, such phases precipitate after suitable heat treatment. So we have to do certain kind of heat treatment if we have to precipitate these phases. These precipitated phases have a strengthening effect on the alloys. So this precipitate which is formed will give more strength to the alloys, and this kind of hardening of alloys actually is known as the age hardening, or also known as the precipitation hardening. So here is the process of the age hardening. It is given here in the figure. So here we discuss the age hardening process. So you can see the percentage weight of copper on the x-axis and the temperature on the y-axis. So around 650 degrees centigrade, you can see there is a solution alpha, and after that there is a decrease, and the solution gets weakened. It follows a certain line which is shown in the curve and given by the line AB. So it is seen that the solubility of copper in the alpha phase solid solution decreases steadily and quite considerably with decrease in temperature, and it is given by the line AB. As temperature falls from this 550 degrees centigrade, what will happen is that copper aluminide CuAl2 is formed. You can see it in the figure. So it is in the range of 400 degrees centigrade temperature and beyond the alpha range, and this is deposited as coarse particles in and around the grains of a solid solution. But this copper aluminide is actually very hard and brittle, so it cannot be very useful as such. So then what we do, actually we will heat the alloy to about 550 degrees centigrade. After this alpha thing cool down, then we are again now reheating it to about 550 degrees centigrade. So what will happen is that copper aluminide that was formed will be reabsorbed in the alpha solid solution, and there will be a single phase alloy like we discussed earlier. Single phase alloy will be there, and this alloy from this state now will be quenched. So now we will not follow the line AB, we are quenching it directly. So then it will follow this dotted line given in the figure, and it will come to the room temperature. So what happens now is that there was insufficient time for copper aluminide to form because our cooling rate was so high. So copper aluminide didn't form, and copper atoms are now held in a supersaturated solid solution within the aluminium. As you can see in the figure, the states 2 and 3, or the points 2 and 3 mentioned in the figure, so represent the supersaturated solid solution. So in that way we have prevented the formation of copper aluminide. So this supersaturated alloy is allowed to stay at room temperature for 5 to 7 days. We are discussing the process, how we have skipped the copper aluminide thing. And the result is that the strength improves significantly because of slow precipitation of fine submicroscopic particles. So this is fineness Like in earlier things also we have discussed, fineness gives us compactness and they have better strength and other properties, and these particles are almost uniformly distributed around the grains. The time of this precipitation may be reduced to a few hours by heating the quenched alloy to 120 degrees centigrade. So if we heat it to a certain temperature, then the time for this precipitation will be reduced, and thus we will have a new thing, that is artificial age hardening. Otherwise it happens in a certain time which is longer, so that's why it is also known as age hardening. But if we reduce that time, then we will have artificial age hardening. Close control of both time and temperature is very essential in this process of precipitation hardening, and for that purpose salt baths at constant temperatures are used. However, this alloy loses its corrosion resistance in hardened state and must be protected by cladding. Suppose it gets hardened, then it will lose its corrosion resistance, and then we will need cladding to prevent it from exposure to different kinds of impurities. So we have discussed till now the alloys of aluminium and aluminium non-ferrous metal. Now we discuss the copper. This one is also very important. So what are the properties of copper? It has excellent engineering properties and very good electrical conductivity and high thermal conductivity also, and applications are like an electrical conductor and as heat exchanger tubes also because of its good thermal conductivity. So how we produce copper? Copper is also extracted similar like in aluminium case. It is extracted from its sulfide ore. Suppose copper sulfide is there, then we will extract it from that. So such ores also contain sulfides of iron. So iron is a very abundant material, so it acts as an impurity in various places. Low grade ore is converted into sulfide concentrate, which is smelted in reverberatory furnace to produce a mixture of sulfides of iron and copper called matte. So when we are doing this copper production, we are getting both iron and copper sulfides, and this mixture is known as the matte. Then the slag is separated from the matte. Then the copper sulfides, then they are chemically converted into impure or blister copper, which is of 98% purity, by the process of blowing air through the matte. So simply we blow air and the copper sulfide is then converted into blister copper. And the iron sulfide, how we separate it? They are oxidized and converted into slag. So they come out in the form of slag. The blister copper is then transferred to a refining furnace. So after separating the blister copper and the iron sulfide, the separated blister copper is transferred to refining furnace, where most of impurities are converted into slag and removed. So again slag is there and it is further removed. So refining is going on. This fine refined copper is then called the tough pitch copper and is further refined electrolytically also. So the refining is done in various steps. Final one is the electrolytic process to produce 99.95% pure copper, and it is known as electrolytically tough pitch ETP copper. What are the applications of this ETP copper? ETP copper contains around 0.04% oxygen, which forms interdendritic copper oxides U2O when copper is cast. If copper is heated to a temperature of about 400 degrees centigrade in the atmosphere of hydrogen, then hydrogen reacts with dendritic copper oxide and produces steam. So this can happen at a temperature of 400 degrees centigrade, and then further what will happen, that hydrogen is there and oxygen is there. So water molecules will be formed, and these being large in size do not diffuse readily and cluster around the grain boundaries. Thus they will cause internal holes. So these water molecules will cause internal holes in the copper, and this phenomena is also known as the hydrogen embrittlement. So it is not good and we need a solution for that. What is the solution? So method of avoiding hydrogen embrittlement are like adding phosphorus in the alloy of copper, and thus what will it will do? The phosphorus will form an oxide, P2O5 phosphorus oxide, and thus it will help us to prevent the formation of water, and hydrogen embrittlement will not be there. And there is one other method, which is to cast ETP copper under a controlled reducing atmosphere. To reduce copper to produce copper, which is oxygen-free high conductivity copper, also known as the OFSC. What are the applications? ETP copper is used for production of wire, wrought, plate and strip, and they are also serve various purposes in industries. Now we discuss about the different kinds of copper alloys. Copper as such forms alloys with different things like zinc. With zinc it is known as brass. With tin it is known as bronze. With tin and phosphorus it is known as the phosphor bronze. With aluminium it is known as the aluminium bronze. With nickel it is known as cupronickel. So these kind of different alloys are there in case of copper. So the first one is known as the brass. This is the first alloy of copper, and we now see cartridge brass. It's the name of brass. So it contains 70% of copper and 30% of zinc. What is its properties? It is soft and ductile, and in anneal form can withstand severe cold working also. So it can be cold work if it is annealed, and it is an ultimate tensile strength of 350 to 600 Newton per millimeter square. So this cartridge brass is used for making cartridges, that's why its name is there, and in condenser tubes, sheet fabrication and for other general purposes. Then there is the Munz metal, and its properties are like 60-40, 60% copper and 40% zinc. In case of the cartridge brass it was 70-30, and this Munz metal ultimate tensile strength is between 400 and 850 Newton per millimeter square. So its strength is somewhat better than cartridge brass, and it is suitable for hot working operations as well as for casting. An addition of 2% of lead will improve its machinability. Also small additions of iron, aluminium, tin, manganese and nickel to 60-40 brass, that is Munz metal, will improve its strength considerably. What are its applications? It is used in cast walls, marine fittings, marine propellers, shafts, pump rods, autoclaves, switch gears and high strength fittings. So it is got a very high ultimate tensile strength, that's why it can be used in such places. And brazing alloys are essentially the brasses of 50-50 composition with the small additions of tin, manganese and aluminium. So these brasses actually brazing type 1 are hard and brittle. So after discussing the brasses, we now come to the second type of alloy, that is the bronzes. So bronze medal you must have heard whenever you compete somewhere, so the third position person gets the bronze medal. So the same bronze is here. The coinage bronze used for making coins in earlier days. So it contained about 95% copper, 4% of tin and 1% of zinc. And zinc actually acts as a deoxidizer, so it can remove the impurity and make this material more soft and ductile. So there is the Admiralty gunmetal, which contains 88% copper, 10% of tin and 2% of zinc. So in case of bronze, tin is the main thing. This bronze is normally cast to produce steam and water fittings and bearings. So it has very good anti-corrosion properties also, because it is used in case of steam and water. And addition of lead improves the pressure tightness of the alloy. So if we add lead, then we can get good pressure tightness, meaning pressure will not leak. Phosphor bronzes are commonly used in manufacture of bearings, hard drawn wires and bronze springs. In addition to tin, they contain a small percentage of phosphorus as alloying element. 0.2% of phosphorus forms copper phosphide, which is a hard compound, and this acts as an deoxidizer and thus helps to improve fluidity. After discussing bronze, we now see the magnesium and its alloys. So magnesium is a light metal with density of 1.74 gram per centimeter cube, and when aluminium is added to magnesium in the range of 3 to 10% with a small amounts of zinc and manganese, then it increases the strength, hardness and castability. Then the composition of magnesium, aluminium and zinc alloys, they have good mechanical strength and corrosion resistance. So these alloys are good casting material and generally used at high temperature like 250 degrees centigrade. Also these magnesium alloys are good casting material and generally used at 250 degrees centigrade temperature. Best advantage that magnesium alloys offer is that of low density, thus they are used in many aircraft parts. Now a very important thing we are going to discuss is the bearing materials. We use bearing in various places for supporting various kinds of loads, whether it be shaft or whatever use we are putting it to. So bearing is very important. We use bearings in those places. And what should be the characteristics of bearings? They should be strong enough to sustain bearing load, obviously, and they should not heat up also rapidly, because that will lead to their wear and tear. They should have low coefficient of friction also, because then they would not take up the load easily, and friction would result in lesser transmission of the force also. And they should wear less. We know that thing, wear should be less, and they should have long surface life, and they should work in foundry also. So bearing bronzes, babbitts and copper lead alloys are the important bearing materials that are widely used in service. So we see these things are used in various places: bronzes, babbitts and copper lead alloys. Copper tin alloys with small additions of other constituents are also used for heavy load and severe service conditions. Advantages in case of bearing bronzes are that they are highly resistant to impact loading. That's why they are used in bearings. They can resist impact loading, and they are particularly used. That's why they are used in locomotive and rolling mills bearings, because there such kind of forces are coming in case of locomotives and all. Bronze line bearings are easily removed, and finished bushings are generally available in stocks. So this is one advantage also. They can be easily removed, and finished bushings are easily available. Disadvantage is that they get heated up fast as compared to other bearing materials such as the babbitts. So in comparison to the babbitts, this bearing bronze gets heated up very fast. So if high temperature applications are there, then we will have to see whether to use it or not. So that's why we are now discussing babbitts. What are the properties of these? So tin, copper, lead and antimony. Actually there's a certain difference between babbitt and other bearing bronzes. Here antimony is coming in. Earlier we didn't see antimony. Tin provides the hardness and compressive strength. Copper in this makes it tough. Antimony prevents the shrinkage, while lead contributes to ductility. So these elements give different properties. Bearing liners are extensively made in babbitts for their better anti-friction properties than other bronzes. And babbitt backed solid metal of high compressive strength gives good service under high speeds, heavy pressure, impact loads and vibrations. The backing material could be bronze or steel. A thin layer of high tin babbitt thoroughly fused to a tin bronze or a steel shell has exceptional load carrying capacity and impact strength. Babbitt bearing linings of dependable strength and life are made by pouring molten material into bearing, allowing to solidify them and fuse thoroughly, and then machining to finished sizes. So this is the process how this babbitt bearing linings are made. While the melting point of babbitt varies between 180 to 245 degrees centigrade depending upon composition, the pouring should be done when metal is in fully fluid state. Otherwise it will be difficult. For example, SAE10 type of babbitt has a melting point of 223, but the pouring should be done not below 440, because if it is very low, then it may have already converted into solid. Suppose it has temperature of 223, then what will we pour then? So the temperature should be slightly higher always. Then we come to the copper lead alloys after discussing the babbitt type. In this case, these copper lead alloys have only half the strength of regular bearing bronzes. So we have lesser strength here, but certainly they would have certain other properties why that's why they are being used. They are particularly advantageous over babbitt. Why? Because at high temperature they can retain their tensile strength. That is very important. So that's why they are used. Although they have lesser strength, but in comparison to babbitt, they are good for high temperature applications as they maintain tensile strength. Typical copper lead alloys contain about 75% copper and 25% lead and melt at around 980 degrees centigrade. The room temperature tensile strength of copper lead alloy is about 73 megapascal and reduces to about 33 megapascal at about 200 degree centigrade. So if the temperature is raised, then its strength goes down. Further moving on to the cutting tool alloys. These are also very important because if we are using certain materials for cutting, then what should be its properties and what should be its strength, we must know that. So there are basically two types. One is called the stellite and the other one is called the cement carbide. So we discuss stellite now. So it's an alloy of cobalt, that is 40 to 60% of cobalt is there. Chromium is around 25 to 35%. Tungsten is 4 to 25% and carbon is only 1 to 3%. And its properties, it has low coefficient of friction. So that is very good because it will not cause friction, so heating up also will be less. And these possess high hardness also, so they can cut other things. Red hardness is also good, and they have high wear and corrosion resistance, so they will not wear also. That's why they are being used as tool alloys. Their desired size and shape is achieved by casting, and no heat treatment is required in these and the production of these type of tool alloys. The hardness for these varies between 40 to 60 RC, that is Rockwell hardness, and they retain their hardness up to high temperature because they do not undergo phase changes. So this is a very important property in case of tool alloys. They do not undergo phase changes, so their hardness is retained even at high temperature, and they can be used for cutting different things at high temperature also. So applications of these stellites are in cutting hard die faces, can surfaces and wear plates. So these can be used for cutting dies even, and these can cut steel at twice the cutting speed of high speed steel. So you can see how the non-ferrous materials are even getting better than the ferrous ones. They are better than high speed steel. They can cut at twice the speed. So cemented carbides now we discuss. Is small pieces with cutting edges and mechanically jointed or braced to tool shank. So these are formed like this, that small pieces with cutting edges and mechanically jointed or braced to tool shank. These are the things. They are made like this, that the small pieces with cutting edges are mechanically jointed or braced to tool shank. Cementite carbide tool tips are produced by a process of powder metallurgy. So this is one process in manufacturing science, you read that, powder metallurgy. So these cemented carbides are made by this process only, and then they are sintered, and these contain the tungsten, thallium and titanium in cobalt powder. The constituents are 40 to 95% of tungsten carbide, 3 to 30% of cobalt, and 0 to 30% of thallium carbide and titanium carbide. The hardness of the tips is in excess of 65 RC compared to 60 RC of stellite. So you can see that cemented carbides are even better than stellite in case of hardness. And the high hardness, high compressive strength at high temperatures are the main characteristics of these cementite carbides. So in this session we have studied about the non-ferrous kind of metals. Earlier we covered about the ferrous metals. So this now completes our unit number 2, which was about the ferrous and non-ferrous type of metals, and in this we covered about the aluminum and its alloys, and copper also, and then we discussed about bearing materials. So further new unit shall start from the next sessions. Thank you very much.